The last topic in pre-calculus, the idea of parametric equations, and I wanted to go through why they're necessary. All right, so let's look at this. There's two ways of looking at this circle, and those two ways are the standard rectangular coordinate, x squared plus y squared equals 16. We could also look at it as a polar coordinate setup where the radius is equal to 4. But neither of these can describe certain situation. For instance, if someone was walking along this circle from this point D at a constant rate around the circle, where would their locations be after a few seconds? The problem with this equation is if you're talking about the person walking from left to right along the top part of the circle, if we move our line segment here, the problem becomes really apparent that there's two locations that this person could be standing at. And that kind of defeats the purpose of finding where this person is as time goes by, as they walk around this circle at a constant rate. So we could, if we wanted to, I guess, solve this thing for y and only talk about the positive square root of 16 minus x squared. So then we're only talking about d. So another problem becomes apparent. I have this ticking off for 1 second. So as we tick off for 1 second, the distance traveled by d in the first second is from here to here, which is quite a long distance. It's like an eighth of the circle. On the next second, we travel from here to here, which is this short little line segment right here, which is shorter than the first second. So if that's the case, and each time we get closer to this top of the circle, it goes slower and slower, this person is not traveling at a constant rate of speed. So that's the second reason that this method isn't going to work. Now r equals 4 is actually even worse because it only has one variable. So we can't do a rate of change involved with r equals 4. The other variable, of course, is theta, but here theta can be anything, so it generates a circle. Kind of like x equals, well, in this case, x equals -3 generates just a vertical line without any y variable associated with it. All right, so let's set up a way of determining the best way to get this thing to be a constant, right? Let me just get rid of a few things. Get rid of my two people. All right, so let's go back to our general circle, and let's add in a few things. Thing number one, a point on a circle. Now this point can be anywhere, but I'm going to just put it there. From this point, I'm going to add in the radius, and I'm also going to drop the perpendicular from that point and draw over the base of that nice little right triangle. So while we're also there, let's throw in an angle. So here's alpha and a triangle. So if we look at alpha as being what we're changing, just the angle itself, and we associate this coordinate with trigonometry, then we can take our angle and let it be the only thing that's changing, and this point will move at a constant rate about this circle. So set it up so it's going at 1 second a pop and see what's going on. Let's bring it back to the beginning. All right, so that's 1 second of travel. That would be 2 seconds of travel. That would be 3 seconds of travel. And if you think about it, that would be like almost 3.14 pi, which will land it right on the -40 here. So as we move this angle at a constant rate of 1 second, or 1 radian per second, we're getting a location or a speed around the circle that is constant. The second thing we're getting is one location. So this is one type of picture that a parametric equation is going to handle. And I'll get into details later of exactly what it means to be a parametric. Basically, it means you're creating two functions, one for the x-coordinate and one for the y-coordinate. So you can see here it says point A, x c angle, and y c angle. where C angle is the variable that I'm changing up here. So as I make C angle bigger, it moves the point around this circle at a very constant rate. Okay, so another picture that we could look at, let's see, let's go with this one. This is called a cyclone. And basically, it's the curve that is generated by your bicycle tire or car tire as it moves around. And the concentration is on one point on the curve itself. So if we look at point A here, and we start moving the circle, rolling it in this direction, what I want to do is find out where this A is going to be located. So again, I set up this one literally to be t, so time goes on. So at t equals 0, we're at the origin. At t equals 1, we're right there. T equals 2, 2 seconds later, the literal position of A is about 1.5 on the XY system. And we get this neat little curve as the tire rotates and then comes back to its starting position. And that would be at about 6.28, which is 2 pi away, which is the circumference of this circle of radius 1. So it generates this cool curve that cannot be described as a relationship between x and y in one equation. The only way to relate this thing is literally parametric. It's the easiest way too. So again, we're talking about the x and y coordinates as being separate functions. Another possibility of looking at parametric is we can do it physics-wise. We have a cannon and it's going to shoot off a projectile with a certain amount of velocity. And we've dealt with this before where the projectile literally was going straight up and straight down. But in this case, I want to shoot it and see where its range is. So I've set this up to be time, velocity, and the angle at which the cannon is fired at. So here I have it set at 29 degrees. It's being fired at 20 feet per second. And time, of course, is going to be measured in seconds. So when t is equal to 0, the cannonball is located at too high. I'll move my cannon a little closer here. All right, so eventually this thing's going to be fired off at 29 degrees. So as I move my time, the cannonball comes out, follows that 29 degrees for a little while, but of course gravity is going to take over and is going to bring it back down to Earth. Now this is also a parabola, just like the motion up and down, but this parabola is a little different. It is the literal location of the cannonball as time goes by. So at about 2.15 seconds, the cannonball has already gone up and come down and landed about 38 feet away from the cannon. And again, this is a relationship between the vertical, which has the gravity involved, and the horizontal, which has that initial velocity involved. So it creates this nice little curve. Now we can increase the angle of the fire. Oops, I forgot to clear it. And bring it back to 0. Let's increase the angle of the fire to, say, 40 degrees. All right, and then fire it off again. And notice this time it goes a little bit further. So we can do a little analysis of a few things. How far it's gone, what's its velocity as it moves through this curve, and how long until it gets to its maximum point. A lot of little information to be derived from this parametric situation. Now, one of the weirder ones that I tried to come up with to describe this is in physics, things don't usually go the way you would expect them. For instance, particles can act in a very strange way near certain types of medium. So I just created this randomly, but it gives you a good idea of sometimes you have to describe something that's absolutely crazy. For instance, here's time again, t equals 0. I have this point starting at A, and when I start moving this thing, you'll see right away that this is definitely not a function. It keeps wrapping in on itself and going all over the place. But we would still like to be able to describe the motion, how fast is this point going, and generally what the picture of it would look like. So again, this is a thing that is set up as a parametric equation. So let me bring it back to the beginning. This is the curve that it actually generates, and it'll follow that curve second by second. And you can tell when this thing is going faster because the distances between the points are further away. And you can tell when it slows down, like right here, because the points are really close together. So you can get an idea of what this object is doing as it fluctuates back and forth and gets further and further away from the origin. And again, this is only allowable with a parametric equation. So let's go back and look at our circle picture. Now, the circle, we were talking about how we were going to change the angle. So one thing I want to change in this picture is I want to change the angle name from alpha to just t. So we're going to allow this angle just to be called t. So we're going to talk about it as time, but again, it's still just an angle, alpha. So if this is t, and the radius of this thing is r, I'll leave it as r even though the radius here is actually 4, then in this right triangle, to find the x, the length of the base of this triangle, and the y, we can use a little trigonometric relationship between the angle, the radius that's given, and the y we're interested in. So the first one I'm going to come up with is for the x. So let's see here, that would be cosine of t is equal to adjacent over hypotenuse, so x over r. And then we get x by itself, and it's going to be x equals r cosine of t. This looks very much like a a polar coordinate system. Over here, we're going to do sine of t, and that's going to equal opposite over hypotenuse. So we'll get y over r. So in this case, we're going to get y is equal to r sine of t. So when we get this set up, then we can say that each coordinate, xy, is related by this parametric equation in a third variable, t, where t, we're going to allow it to go from 0 all the way up to 2 pi, but that just brings us back to the beginning, so we get that. Now one nice thing is as theta opens up, our point is going in a specific direction. That's called orientation. So unlike x squared plus y squared equals r squared, that can be plotted in any direction by just choosing any x's that you want. Usually people go from negative x to positive x and plot the circle kind of going in this direction. With parametric equations, you're fixed on going in this direction because we're starting with time is equal to 0, and then we get time equals 1, time equals 2, time equals 3, and we get this specific orientation as we rotate around this circle. And in this case, this parametric equation, literally written as 2 parts, is considered counterclockwise. So because it's moving the opposite the way a clock will move, we're going to call it a counterclockwise rotation, or an orientation that moves it in a counterclockwise fashion. So parametric equations have this idea of orientation, so we can follow the path in a specific direction as t increases. So let's look at a parametric equation that I've already set up. So here I have the x-coordinate is going to be the square root of t plus 1, and the y-coordinate is going to be t over 2 minus 3. And I have t starting out as 0, which kind of makes sense. At 0 time it shouldn't have gone anywhere. And then as time increases, I want to see the behavior of this graph. So I'm going to do by hand just a few of the points, and then I'll show you the rest of the answers done by a spreadsheet. All right, So let's see here. If we plug in 0, that's a good one to try. So 0. 0 plus 1 is 1. 0 over 2 is 0, minus 3 is negative 3. So the first coordinate on this graph is 1, negative 3. So here's 1, negative 3. All right, the next point I can try is 1. I can take square roots of 1. So that would be 1 plus 1, which is 2. This will be a half minus 3, so that's negative 2.5. And we would have a coordinate 2, negative 2.5. Right about there. Now the nice thing about this is just by those 2 points, I have determined that the orientation of this graph is that direction. So it's moving left to right. So it kind of gives us the orientation. So we know that this graph is going in this direction and it cannot go backwards. All right, the next point of interest will be this 4. I can take square root of 4. So square root of 4 is 2. 2 plus 1 is 3. And then 4 over 2 is 2. 2 minus 3 is negative 1. So we'll get this coordinate 3, negative 1. So the graph is continuing in this direction, and it cannot change direction. That's the orientation of it. And this is the third point. So one way of labeling these points, this would be t equals 0. This one would be t equals 1. This one over here would be t equals 4. And the other way, of course, is labeling them by the coordinates. All right, down here to 9, the next nice square root. Square root of 9 is 3. 3 plus 1 is 4. 9 over 2 is 9 halves, which is 4.5 minus 3 leaves us with 1.5. So at 4, we're up to 1.5. And again, this path is continuing in this direction, and the orientation is that way. And this is t equals 9. All right, so if we look at what this would look like with all the points, we would have 0 through 10 here. These are the x and y coordinates. This is t equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 at 1.5, and then finally up here at 10. So we're getting this curve that's generally going in that direction, and the orientation is moving it along in this direction. So it's moving from left to right. And we can change the orientations of these graphs. It's not a lot of fun, but I could change this around so it's actually going from A way up here and ending down here. Sometimes it's possible to take the equation that's parametrically written and write it in standard form in rectangular coordinate systems. One way of doing that is to take the x-coordinate and solve it for t. So if I take the x-coordinate, which is the square root of t plus 1, and I start solving it for t, I'm going to get the square root of t is equal to x minus 1. Square both sides, and I'm going to get t is equal to x minus 1 all squared. And upon finding that, I take that and plug it into the y-coordinate. So here we have y is equal to x minus 1 all squared all over 2 minus 3, which is a parabola that has been transformed 1 unit to the right, 3 units down. And this 1/2 is a dilation. It's going to make it a little bit lower, flatter, closer to the horizontal. So if I was just going to draw a quick sketch of this, we would move 1 to the right and 3 down. We'd have a nice little point here. This is the vertex of the parabola. I could find the y-intercept. Let x equals 0. We're going to get a half minus 3. So that would be 2.5. So it would hit here. The axis of symmetry would go right through that point. We'd also end up over here at 2, negative 2.3. And we could find the y intercepts and whatnot, but generally you would get a nice little parabola that comes down and does that. So this would be the graph of the function here, but the parametric equation is only dealing with this point and moving literally in this orientation direction. Every point is moving in this direction as we go up the graph. So even though we can write it as a rectangular coordinate system, the parametric equation is still only a part of it. Like the circle, another important parametric equation is actually the simple line. And with a parametric equation, it just changes a little bit. So let's talk about this kind of in detail. All right, so we have here, y equals mx plus b. And I wrote m as the change in y over the change in x because, that's what slope is. So if we start here at point A, to get to the point B, the ratio in the change in the x values compared to the change in the y values becomes the slope of the line. Literally change in y over change in x. Here I have the slope is positive, and it really doesn't matter which side you draw the triangle on. If you want the literal change in y, change in x to go along the top, that's fine too. But with parametric equations, what we're trying to do is we're trying to come up with the coordinates as a separate function of t. So as the way I kind of think about it is, if this distance is covered horizontally when t is equal to 0 to 1, then this length of this line is going to be the change in x times t. If this took 2 seconds to go that distance, then it would be 2 times the change of x, and the same thing would happen to the change in y. So one way of looking at x is it's the change in x times t. Of course, that just gives us that length. We need it to start at a specific location. In other words, when t is equal to 0, we want this thing to start at A. So if we give A the coordinates as an initial coordinate, x sub 0, y sub 0, and we ignore this part of the line completely, so this is more like a ray because it's going to go in that specific direction. So our orientation would be rising along this curve left to right. We would say that it would be delta xt plus x sub 0. So that when t is equal to 0, wipes this term out, and all you are at is the beginning point x sub 0. The same thing's going to happen for the y coordinate. It's going to change according to this change in y, and it's going to be according to how much time has gone by. So after 2 seconds, your change in y would be twice its height. So this would be change in y times t plus the beginning point, which is y sub 0. So one of the nice things about this line parametric equation is we can change the orientation pretty quickly. And the way we would go about that is instead of choosing A as the beginning point, what if we chose B as the beginning point? And we go the opposite direction. So if we start off here with x sub 0, y sub 0, then from here we're going to change x going backwards. So we're going to start up here, we're going to change x backwards so it'll be negative change in x and negative change of y. So then we would have x is equal to negative change in xt plus x sub 0 at the b coordinate, and y would equal negative change in y of t plus y sub 0. And that would just reverse the orientation of the graph. It would get rid of this part, and your points would constantly be moving from right to left in a downwards direction. So this idea of orientation and being able to change it is kind of important, especially if you're describing a particle that's moving in that direction.